of 1/2. Okay, and capital F of 1/2 is the sum, k equaling 0 to infinity, of 1/2 raised to the kth power. Okay. Now again, we have this infinitely long sum here, and we're pretending that we don't know how to divide by fractions. Okay, but we have made the discovery that if the absolute value of x is less than 1, 1 over 1/2 is going to equal 1 plus 1/2 plus 1/2 squared, 1/2 cubed, and this goes on forever and ever. Okay. Now, again, in our pretend world here, we don't know how to divide by a fraction, but what we can do is we can approximate one over 1/2 as, let's say, equal to the sum. Well, you know, like let's do the first, you know, 4 terms right there. 1, 1/2, 1/2 squared, 1/2 cubed. So our approximation for the square root of 1/2 is going to be 8 plus 4 plus 2 plus 1 all over 8. You like how I did all that in my head just like that? Okay. And this number is 10. This is going to be 15 over 8. Okay. And so then these old time guys, they would have gone, okay, 8 goes into 15 one time and 8 left over. Then you have a 7. So 1/4 is 0.25. That's 1/4. So 1/8 is going to be 0.125. And I have 7 of these things that I need to write down. So what's 7 times 125? I'm trying to do this, you know, without reaching for anything. Carry the 3, 14, 0.17. Carry the 1.
7.5.
Okay, so our answer is 1.875. Not a very good approximation for the number that we know is equal to 2. Okay, now we see that if we use what we're going to call the nth partial sum of x to be the sum k equals 0 up to n of x to the n to approximate 1 over 1 minus x. Okay, and the observations that we can make here is that if n is increasing, the Sn starts trying to get closer and closer to the real answer of 1 over 1 minus 1/2. Okay? All right, so if we lived in a world where we didn't know how to divide by a fraction, then here's a way that we can approximate this number. Okay? So far, so good? Everybody with me there?
Yes.
Yep. Okay. Now, let's pretend we live in a world where we don't know how to find the square root of a number. Oh, wait a minute. That's not pretend. That's the world we live in. There is not a human being alive that knows the square root of 17. Not Terrence Tao, not Ed Witten, who's probably the smartest person alive right now. None of those guys. The square root of most numbers that you're going to put in here is irrational. Okay. So what our goal here is going to be, we want to find some power series. Let's call it capital F of X, which is going to be the sum k equaling 0 to infinity. Then I'm going to have these coefficients and these guys. Okay. So the goal is to find some power series where the square root of x can be represented by this infinitely long power series. If we can find such a thing, then what we'll do, like we did with the above example of dividing by fractions, we will truncate it, okay? And then approximate. Okay, so this is how your calculators work. They're depending on what, and we'll get to the square root probably tomorrow or Thursday. But what we're going to try to do here, so you find this square root. So like a guy like Turing, you know, the guy that invented the first calculator or whatever, you know, maybe his device, like when you do the square root of 2, maybe his device could only spit out 2 decimal places, I guess. And so maybe like the first couple terms of this infinitely long polynomial are good enough. Your book has a few problems where he mentions Ramanujan, and Ramanujan had discovered some of these series that converged so quickly that anytime a new supercomputer gets built and it needs to be tested just to see if it's working or not, they use these Ramanujan identities. And let me find them for you. They're in the exercises. Exercise number 42 and 11.6. He said that Ramanujan discovered that 1 over pi is equal to 2 radical 2 divided by 9801 times the sum from 0 to infinity of 4n factorial. This is a weird one. 1103 plus 26390 n, all divided by n factorial. Looks like to the 4th power. I need to turn the light on in here. Yeah. And then 396 to the 4n. Okay. So this series converges to whatever the number 1 over pi is very, very rapidly. And there are a lot of others that Ramanujan discovered. And the story about Ramanujan, he's an Indian from India, back when India was like I guess a colony or whatever you call it of Great Britain. And he's born poor, illiterate kid, and then he is in a abandoned British building and he finds a math book on the floor. teaches himself to read so he can do stuff in the math book. And then he starts just coming up with his own results, shit like this that I just wrote down. Okay. And then he sends a letter to this Professor Harding, and you've seen the movie. Okay. So anyways, some of these series that we're going to find for these functions might take a long time to converge to a place that we would like, and other ones might converge very quickly. Okay. Okay, so what we've started with here is this function f of x equaling 1 over 1 minus x. Okay. And it agrees with our capital F of x. I forget which way I'm writing these things now. Maybe I should just stop doing it. K equaling 0 to infinity of x to the n, as long as the x in magnitude is less than 1. Okay, so by just manipulating this thing, we can get all kinds of results. Okay, like for example, what if I wanted to find a series representation for this? Okay, now you guys that are computer programmers and stuff, what you're going to learn later on is that computing devices, they start to lose information with division and also subtraction. I remember Professor Chabelle, showing us this kind of stuff. Senior level numerical analysis course. But anyways, what we'll do here is we just write it like it looks, and then directly plug this in to that sum, 0 to infinity of negative x to the n. And so we get the sum 0 to infinity, negative 1 to the n, x to the n. And for that matter, for example, let's say that I wanted to figure out a power series representation for this. Okay, well, what I could do is I could write this as 1 over a plus x minus a, right? And then put this into the sum 0 to infinity. It's going to be, because of this plus right there, it's going to alternate negative 1 there, and then x minus a to the k there. Okay, so that's what this section of the book is all about. It's going to be just doing as much as we can on the cheap, okay? Because I have to just continue on with these things. Let's say I wanted to look at 1 over 1 plus 4x. Okay, well, I do the same little trick I did earlier. 1 minus negative 4x. Plug it into our geometric series deal. That's going to be negative 4x to the nth power. And then just break all the ingredients apart. Okay. Negative 1 to the n, 4 to the n, x to the n. Okay. Now, other types of things that you can do is, let's say that I had x divided by 2 minus 3x. Okay, so there's a couple different approaches here. I can take this x and write it here, okay? And then I'm going to write this thing as 1 over, I'm going to factor the 2 out of it. And what's left, I'm going to get 1 minus 3x over 2, which is going to be x over 2 times 1 over 1 minus 3x over 2. So now we do our thing, x over 2. Okay, and then it's going to be the sum and equaling 0 to infinity of 3x over 2. Because it's a minus there, we don't have to include the minus sign to the nth power. Okay, so then that's going to be x over 2 times the sum, 0 to infinity, 3 to the n, x to the n, over 2 to the n. Okay, now because this is a geometric series, it's absolutely convergent. So that means I can distribute this thing to the inside. Okay, remember, converging positive series are always absolutely convergent. So now this is going to go 3 to the n, x to the n plus 1 divided by 2 to the n plus 1. Okay. By the way, guys, first pitch is at pretty soon here, so might want to get your TVs ready. Okay, so here is a power series representation for this function guy up here. Okay. Other things that we can do, like for example, and this is all the kind of stuff that James Gregory was doing. You know, he would take these things and he would try to find infinitely long sums. Now he wasn't, you know, he was more interested in like square roots and stuff like that, which will be the topic for next time. Sine and cosine. I think he actually extracted a bunch for sine. He did a lot of things and got very little credit for it. So let's suppose I've got this function f of x, and it's going to be 1 over x squared plus 2x. All right, so I want to get some kind of a polynomial representation of this function for whatever reason, okay? So if I complete the square in the bottom, I can go 1 over x squared plus 2x plus 1 minus 1, which is going to be 1 over x plus 1 squared minus 1. Okay. And then that's going to be negative 1 over 1 minus x plus 1 squared, which is going to be negative the sum n equaling 0 to infinity of x plus 1 squared to the n, to the 2n. Okay. So this is an interesting consequence of something. So if we start picking this apart here, This 2 is going to make everything positive on the inside of this guy. You guys agree with that? So that means with this negative out in front, everything is going to be negative. All right, so this is some kind of a representation of it, but I don't know how good of it is. Okay, so this, kind of food for thought there. All right, so let's see here. We look at a few more of these guys. If I was to, like, say, f of x is equal to x divided by 2x squared plus 1, I'm just going to write this as x. This problem's easy. 1 plus 2x squared. Okay. Maybe I'll write it as x times 1 over 1 minus negative 2x squared. And now we rhyme it into the formula. The series for this guy, 0 to infinity, and it's going to be negative 2x squared to the nth power. I'll go back to black. Okay, so that's going to be x times the sum 0 to infinity, negative 1 to the n, 2 to the n, x to the 2n, and then distribute the x into the sum to get a proper power series. Negative 1 to the n, 2 to the n, x to the 2n plus 1. Okay, now, where does this guy converge? Where does this series converge? Are the Dodgers playing tonight too? Should look.
No clue.
Well, the next game is against Houston. So, want to see if they start throwing at them. Hold on, LA Dodgers. Yeah, they are. I wonder if they've thrown at anyone.
What's going on? Why are you saying thrown at anyone? Are they?
Well, remember the Astros were cheating when they won the World Series against the Dodgers.
Yeah.
They had these buzzers on their uniforms knowing when a curveball was coming. That game where Darvish just got lit up, it's like they knew what pitches were coming, and now we know they did. So now everybody's talking, okay, what's going to happen when they, when they play them?
So do they get their championship revoked because they were cheating? How does that work?
Not yet.
Oh, wow.
They just swept it under the rug. Kind of said, well, it's going to have an asterisk by it forever. Altuve's MVP will always be questioned. Everybody was real anxious to see him hit this year because let's see if he's as good as that, every year hitting 330. Okay, well, anyway, so for this guy, we look at the thing that we were adding up, negative 2x squared in magnitude has to be less than 1. So that means that 2x squared is going to be less than 1. So x squared is going to have to be less than a half. So that means negative 1 over radical 2 less than x, 1 over radical 2. So the interval that we can use here for convergence, just to start, is this interval. Okay, now yesterday and last week, I was saying that, with these power series, we always have to check the endpoints. Okay. Well, that's true if it was anything other than a geometric series, because we know that for a geometric series, if this is going to converge, whatever that blob thing is has to be in magnitude less than 1, and the endpoints never work. Okay, now we're going to see something kind of bizarre happen here in a few minutes with something like that. Okay, so for all these other problems up here, if you like scroll back to, this guy here, we would have to have 3x over 2 in magnitude less than 1. So that would mean -2 less than 3x less than 2, -2/3 less than x less than 2/3. And then I'll leave it for you guys to rationalize to yourself that you don't have to check the endpoints because it came from a geometric series. Okay. All right. So there we go. So the basic stuff we kind of have gotten out of the way. And, pretty much anything we want to do, we can. Like, for example, if my function f of x was 1 over x squared minus 2x plus 3, we would write it as 1 over x squared minus 2x plus 1 plus 2. And then we would write it as 1 over x minus 1 squared plus 2. And then we would factor 1/2 out of this and go, this is going to be 1/2 times 1 over 1 plus x, come on, right, x minus 1 squared all over 2. Okay, now let me really get in here with this. 1/2, then it's going to be the 1 over 1, whoops, I meant to say minus negative x minus 1 squared over 2, like so. Okay. So as long as I did all my factoring stuff correctly, that's what I get. Okay, so now you just shove it into the series. And my advice is don't try to simplify too much at once. Just put the whole blob in there. Negative x minus 1 squared over 2 to the n. Okay, now is when we start making it look pretty. 1/2 sum, and then it's going to be from 0 to infinity, -1 to the nth power, x minus 1 to the 2n power, divided by 2 to the n. And our final guy, 0 to infinity, -1 to the n times x minus 1 to the 2n divided by 2 to the n plus 1. And again, in order to decide what x's we're allowed to use for this thing, we take the whole thing that we used, negative minus 1 squared over 2, and that has to be less than 1. And so this means that x minus 1 squared less than 2 So -2 less than, whoops, negative, sorry about that. Negative radical 2 less than x minus 1 less than radical 2. So the interval that we can use here is the numbers 1 minus radical 2 up to 1 plus radical 2. Okay, now 1 minus radical 2 in magnitude is less than 1. 1 plus radical 2 in magnitude is bigger than 1. But those aren't the numbers that we're plugging in. What we're doing is we are going to subtract 1 from the number and then go. And then we're going to divide it by 2 on top of everything else, okay? All right, so this is how we deal with just these straightforward, power series things, okay? So for a different problem, what if we had the function f of x equals tan inverse of x? Now, the only reason I'm using this is because of it has such a nice looking derivative. The derivative of tan inverse of x is 1 over 1 plus x squared, which we can write as an infinite sum from 0 to infinity. And then it's going to be -1 to the n, x to the 2n. Okay, and this is going to be valid as long as the x squared in magnitude is less than 1. That means that the x has to live between -1 and 1. Okay. Now, what kind of numbers do you put into tan inverse? Let's see here. The tan inverse, if you graph the tangent function, it has these guys, right? Asymptotes. And that's happening at pi over 2. And the graph of tan inverse is going like this. I mean tan. So this is y equals the tangent of x. X-axis, y-axis. Okay, so the tan inverse then, what we do, we plug an angle in for tangent, like pi over 4. Okay, and somebody answer this question without reaching for a calculator. What's the tangent of pi over 4? Do not reach for a calculator.
1.
1. Okay, so the tan inverse of 1 is going to be pi over 4. Okay, so on this graph that I'm drawing here, what I'm obviously going to try to do is I'm going to try to then integrate this series to get back to the original. Of course, we're going to have to write it as a theorem. All right, but I want us to point out here that I can't use the number 1 right here in this series, okay? So our domain is going to have some kind of restriction to it. All right, okay, so now the next step is that if the derivative of tan inverse is equal to 1 over 1 plus x squared, which is now written as this sum -1 to the n, x to the 2n, then the tan inverse of x is the integral of dx over 1 plus x squared. Okay, so that's now going to be the integral of the sum. Okay, now I'm pointing this out to Eduardo and anyone else that might be interested in more and more math. So, can we interchange the sign of sum and integral? These are questions that you continually ask as you go up the food chain in math. What can I bring outside of an integral sign, bring inside to an integral sign? Okay, now if we can do this, and this is a big if, okay, it's true anyway, but if this is equal to then the sum of each of the integrals, that's just a something, 2n dx, what we're going to get is then the tan inverse of x is going to be this infinitely long sum of this integral, which is -1 to the n, and you just do the stupid integral, x to the 2n plus 1 divided by 2n plus 1, and there's a constant c. Okay, now here we have to get the constant, okay? So when x equals 0, do this in red, if x is equal to 0, the tan inverse of 0 is 0, okay? And when I plug 0 in for x here, I'm going to get 0 plus c. So that means that the c is equal to 0. Every now and then you get one of these guys where it doesn't exactly work like that. Okay, so that was kind of a big ask, to do that. So let's write the big result down here. Okay, it turns out that we're allowed to do this, okay, as long as certain conditions are met. Okay, so here's our theorem. Okay. So let's suppose that we have this power series f of x given by the sum. Oh shit, trout. I lined into a fucking double point. So, and I won't even put the the counters there. Cn x minus a to the n. Suppose this has radius of convergence r, which is positive. Okay. Then f is a c infinity function on the interval a minus r to a plus r, where f prime of x, which is the derivative with respect to x, this is result number 1, of this sum okay. And the punchline for part one of this thing is that I can move the d by dx to the inside. And then we just get the normal n cn x minus a to the n minus 1. Okay. And furthermore, this power series for f prime of x has radius of convergence r, where it's the same r. Okay. Result number 2 is the antiderivative. Okay, the indefinite integral of this f of x dx is the indefinite integral of the sum cn x minus a to the n, which is now, here's the big punchline, I can interchange this and this. In advanced, more advanced math courses, I guess I have to throw dx in there. Okay, so now we just do it. These more advanced courses, you're trying to like invert integral equations. And knowing when you can interchange signs is a huge, huge plus, okay? So this is the sum of, then it's going to be cn x minus a to the n plus 1 divided by n plus 1. And this series has the exact same radius of convergence r. Give you a second there to maybe catch up. Okay, now what happens with these guys is that sometimes an interval works, I mean, an endpoint works and another endpoint doesn't, but then when you take the derivative or you integrate it, sometimes those things work themselves out, okay? We go back to the tan inverse example. We had 1 over 1 plus x squared's derivative was the derivative of the sum 0 to infinity, negative 1 to the n, x to the 2n, like so. I don't need the equals this. I don't need these guys. Okay, nor do I need that. Okay, so the tan inverse of x derivative is therefore this sum, 0 to infinity, negative 1 to the n, x to the 2n, like so. Okay, so that means that if I, according to the result up there, the tan inverse of x is then going to be this series over 2n plus 1. Okay, now, again, when you guys are doing this and someone's paying you for it, like maybe get into this 40-year-old code because it's exactly what we need to do this job. Okay. Well, you're going to have to kind of get in and make sense of, all of the, you basically have to write down all the math, and then you're going to have to check and see if it can be applied to whatever the hell your boss is wanting to apply it to. Your boss might want to put in numbers that just, they're not going to work. And you're the smart person, you're the math person in the office. Everyone else is sales. They're making millions of money, millions of dollars. You don't make shit because, all us guys that are good in math, we should all like unionize, and then we just say, okay, you want something solved? That'll be $1 million.
Yeah, but salespeople are a lot easier to replace.
My brother-in-law is just over here, and he works for PIMCO. You know what that is?
Yeah.
Yeah, so he's an accounts manager guy, and he sees how much these executives, like their bonuses are just millions of dollars. All at this, like he was just complaining right now, man, I don't make shit. But all of us that, if we can just kind of stick together and not give away the math anymore, like this class, don't even have it. Like, you want to learn any of this stuff? This is how it was in the 1500s, like when Cardon and Tartaglia were having competitions to solve the general cubic. A lot of these guys kept their discoveries to themselves. Fermat was like that as well. Okay. Anyways, this is going to converge as long as you remember that the x had to live between -1 and 1. Okay. All right. So on the tan inverse graph, this is like the first graph you see that you have two horizontal asymptotes. Back in algebra 2, we say there are some things out there that have double asymptotes. College algebra 2, nobody ever sees them because that's all trig. Okay, so the graph of the tan inverse guy goes like that. Okay, and this value up here on the y-axis is pi over 2, and then this is negative pi over 2 down here. Okay, so the tan inverse of infinity would therefore be pi over 2, I guess. Okay, now this is where pi over 4 came from. And if I go over here, that's where the 1. Okay, tan inverse of 1 is this pi over 4 value. Maybe I should raise it a little bit. Okay. So the only values that we're allowed to use are between -1 and 1. So that means that the outputs, the tan inverses of x, would live in the negative pi over 4 to pi over 4 range. Okay, so let's say that you had a problem that you're working on, and the way you've set things up, your angles are all kind of small. Well, then this series right here would be one way to approximate the tan inverse of x. You would just truncate it off somewhere. This is exactly what your calculator is doing. Now, that's a little bit more complicated than that. There are if-then statements that go on. I'll explain as we get there. Okay. And so if our angles are living, like, let's say the way we set things up, our angles are going to be living between maybe pi over 4. I've told you guys, some of you that have been with me now for 3 classes, some of these stories where the way we set things up in the physics course to take advantage. Oh, Shohei's hitting. Let's say if he's as shitty a hitter today as he was a pitcher yesterday or 2 days ago, he sucked. He didn't even record an out. That blows. Give him all this money. I could have got someone out. Well, probably not. But anyways, so obviously we can't, if this is what we're expecting answers to look like, we're not going to be able to use this. Okay. So we would have to manipulate the series a little bit in order to get what we want. Okay. We go up to this theorem thing up here. The proof of this is, it's just tedious. I mean, I've gone through it once, and then it's not even in the book, so I had to dig for it. It's somewhere in my notes somewhere, but it's not a penetrating proof. You know, it's just the proofs that I do for you are the ones that I think, you know, are worth watching, especially for the math majors. I figure I got to do something for them, you know, and the physics majors, because anybody a physics major out there tonight in class? Well, you're going to have to take as much math as all the math majors, so you might as well double. Okay.
Sounds like one person.
One person? Okay, one physics major. All right, so this kind of is a good start here. Here's our logarithm function again. Let's let f of x equal the natural log of x. Okay, now as it stands right now, the x's that we're allowed to use in this are from 0 to infinity. Okay, now here we go again. Do we live in a world where we know how to get the natural log of 5? Is that something that our human brains can do?
No.
No. It's an irrational number. The reason that we can't do these things, like nobody knows what the value of pi is. You start getting into these like Plato type arguments where, you know, pi exists as its perfectness of pi in the shadow world, you know, of Plato's. You ever try to read that thing? That, you know, it's these people and all they see are shadows on a wall of a cave, and he's relating that to, they don't know what the actual things look like. They only can see the shadows of them. Did you ever have to read that in high school? I did. And reading that made me feel carsick. Like I just fucking hated that. But anyways, because pi is irrational, no one knows it. Okay, we can approximate it. Okay, so we want to get some kind of a series for this, because after all, we are interested in solving finance type equations where we need to get an exponent down. So we take our f prime of x and we get 1 over x. Okay, now look at what the difference is. The original function was defined on the half real line, the positive stuff. The derivative is now defined everywhere except the origin. Okay, so now what we want to do is think about what kind of numbers are we going to be taking the natural log of? Well, let's say we were going to be taking the natural log of numbers that are like between 1 and 2, let's say. All right. So what we can do with this is we can do that trick. I can go 1 minus 1 plus x. And then this is going to be 1 over 1 minus 1 over 1 plus x minus 1. And write that bigger. write this as 1 plus x minus 1. Okay. Now the series that we use for this is going to be this alternating guy. So it's going to be -1 to the n, x minus 1 to the n. And this is valid when x minus 1 is less than 1. Okay, so that means that -1 less than x minus 1 less than 1, 0 less than x less than 2. Okay, can't use 2. I mean, we can't use the number 0, thank God, because we don't want to plug 0 into a logarithm anyway, right? Okay, and apparently if we want to use this to approximate the natural log of 2, we might have some issues. Okay, so now our f of x, which is going to be the antiderivative of f prime of x, I'm just going to take this sum and integrate the x part of it. So it's now -1 x minus 1 to the n plus 1 over n plus 1. Okay. And I can get rid of the n plus 1 stuff if I start the counter at 1 and go to infinity. Now I'm going to have to change this guy, but this one, x minus 1 to the n, divided by n. And the radius of convergence, r, is equal to 1. And the interval that we were using, 0 less than x less than 2. So if we check the endpoints, we know up here, in this guy right here, we can't use the endpoints. But when you integrate or take the derivative, sometimes that changes. The only thing that remains a constant is the radius of convergence. You'll never be able to make that a little bit bigger, okay? Okay, so if x equals 0, then I have the sum -1 to the n plus 1 times -1 to the n divided by n. So this is the sum -1 to the 2n plus 1 over n, which is the sum. Because this is an odd number, 2n plus 1, that's always going to be -1 over n, and we diverge. If I try x equals 2, I'm going to get the sum -1 n plus 1, 1 to the n divided by n. That converges, alternating harmonic. Okay, so here's what we've just discovered. For x in the interval 0 up to 2, close it off like that, the natural log of x agrees with this series, n equaling 1 to infinity, -1 to the n plus 1, x minus 1 to the n, divided by n. And note that when x equals 2, we get that natural log of 2 is equal to, once again, this alternating harmonic series. Now, the convergence of this guy is pretty damn weak, right? Because I showed you I can rearrange it and get it to add up to something else. Okay. All right, so before we expand on this, let's take a 10-minute break because I got to eat something. I forgot to eat today. So, 10-minute break. Okay. All right, I'm back. I had to eat something. Having this contest with my friend. I keep weighing 202 pounds every morning. We're working out, and he's just above 220, so we're having a contest to see if he can get under 220 before I can get to 199. And when I'm eating, I think, is the problem. So I need to eat like now and not at 11 at night. Okay, so that's what my life's turned into, a weight loss contest. All right, so let's go back to this guy and see if we can maybe do something with it to get the log of 3. Okay, so back to our f of x equaling the natural log of x, sorry. Now, by the way, I'm only going to be in this section tonight, okay, this 11.9. I really want you to really immerse yourself in this stuff, especially those of you that aren't, you know, Brian, you said that you're probably going to take a break from school. So this stuff you're going to have to relearn. It will not stick with you. All right. For the rest of you, if you just can just bury yourselves in this, then by the time you're actually using it, and you might even, depending on if Faridi ends up, Faridi is usually, doesn't he have the reputation of being the hard one in the physics department? Is it Faridi? You guys even know?
I hope not. I have him next semester.
Yeah. He's been there the longest. Can't retire because personal reasons, but anyway. So back to this guy, the natural log of x. What we did is we did the f prime of x business, which was equal to 1 over x. And instead of adding and subtracting 1 like I did up there, what if I add and subtract just a different number, a minus a plus x? Okay, where a is some number that I'll determine here in a little bit, or figure. Okay, so now we'll manipulate this as the a plus x minus a. Then I need to factor out a 1 over a. So that's going to be 1 over 1 plus x minus a over a. Now we use the series for this guy. Goes from 0 to infinity, negative 1 to the n. Anytime it's plus here, it alternates. And then it's x minus a over a to the nth power, which is going to be, why did I put a half there? That's supposed to be an a. Okay, so now it's the sum from 0 to infinity, negative 1 to the n, x minus a to the n, divided by a to the n plus first power. And in order for this to converge, we have to have this thing in magnitude less than 1. Negative a less than x minus a less than a. So if I add a everywhere, I get this. Okay. So if I want to find a series for, let's say, the natural log of 3, then it looks to me like we can use a equals 2 if we want. Okay. All right, now back to the problem at hand here. Okay, so remember that this was the derivative. So that means that the natural log of x is going to be the integral of this, which we know we're allowed to do term by term, 0 to infinity, negative 1 to the n, x minus a to the n plus 1, divided by a to the n plus first power times, maybe I should move that, divided by n plus 1, and then multiply that by a to the n plus 1. We got a runner on second and no outs. We'll figure out a way to not score that one because we're the Angels. Okay, so this is now our series. Okay, so you can kind of start seeing perhaps what happens in like a crude program. Okay, so I grew up with Pascal. That's the programming language I learned and have since forgotten. But I do remember doing a lot of if-then statements and stuff, Okay, so let's say that on our device, we want to compute the natural log of 17. Okay, so if we wanted to, oh, by the way, let's check the before we do the natural log of 17. Let's check the endpoints again. Okay, and so when x equals 0, that diverged because it's -1. Well, no, I can't necessarily say that. I got to actually plug it in. So it's going to be the sum, -1 to the n, and then it's going to be -a to the n plus.
Did he cut out for everyone?
Yeah, I think he did just cut out for him.
Okay.
Yeah, I can't hear him.
Well, class is dismissed, guys. Thanks for joining. I'm Bobby too, so I guess we're gonna have to be here. Wait for him to come back in.
How you doing, Brian?
Good. Wishing this class wasn't every day. I'm kind of hating that I took it over the summer, but whatever. It's gonna be done soon, man. How you doing?
I literally missed like the 6 minutes worth of class. I literally took a nap because I had food coma. I had shawarma, and that hit me hard.
Yeah, man. There's just a lot to this class. I think it seems like they're talking about this physics professor. And for physics 2 lecture and lab, it's this Faridi guy. I didn't hear him mentioned. Are any of you guys taking physics? I'm
taking physics in this fall.
I don't think it's necessary for software, but I don't know. I was just talking about you today, and he
Not for software. I don't think for software, but since I also want to get my engineering degree with my math. So it's literally like if I go for my engineering degree, it's literally 3 more classes to get the math degree. So it's like, why not?
Yeah, it's kind of crazy how much math so many other degrees require, to the point where it's like you could, if you don't mind taking an extra, between 3 and 6 classes, a lot of engineering majors can get a double major as a math major, which is kind of crazy.
It's super crazy, and my wife looked at me like I'm fucking insane, like for doing another 6 math courses.
Yeah.
Because it's 3 more here, and then I have to do 3 more at university level.
Oh wow.
So it's like.
Yeah. Go ahead, sir.
Yeah, no. So it's like, why would you do that to yourself? I'm like, because more money.
Yeah. I mean, if it's like 3 classes, that's like not even a whole. I mean, that is probably going to be a semester because it's math, but it's not that big of a deal. It's 3 months. But yeah, if it was like a totally different thing and you were double majoring in sociology and math, I'd be like, you're crazy.
How long was I gone?
Quite a bit of time. We have the last thing on our paper was -1 to the n minus a n plus, and then you stop.
Just n plus 1, I believe.
I was assuming 1 as well, but there's not even there. So.
Okay, let me figure out where I'm at here.
I wish it would just at least let you continue drawing when it cuts you out. I don't exactly understand why your screen freezes.
Yeah.
Because normally when people cut out a Zoom, everything gets lost. It doesn't freeze on a picture. Oh, there we go. Okay, we're at the oh wow, actually we're quite a bit up. Wait, go down. down the opposite way, wherever you're going opposite of that. Yep, down, 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 down. We are right there.
Yeah,
That
no,
where
but-
x equals
well,
0. X equals 0. And you don't have
But-
that other thing in a box. When we were doing it, you did not have that natural log.
Okay. Okay, so what I'm doing here is I'm checking the two endpoints. Okay. And so I check the two endpoints, and so the conclusion that we reach is that this power series represents the natural log of x as long as the x's live in this interval. Um, 0 to 2a. Okay. Now, what we're gonna start learning here, like maybe tomorrow, is that the further away you get from the center, generally the longer it takes for your series to converge to whatever it is you're trying to compute. So you generally want to stay in the middle somewhere. Okay, we pushed a run across. We got runners at the corners, drops up. Okay, so as I was kind of talking to myself, so back when I was like in school and I had to program like in Pascal, the first computer programs that were ever written to do these kinds of things were done in like Cobalt, Fortran, Pascal, and there's probably even stuff older than that that I never even heard of. Okay, but you can see like this formula could be stored in your calculator in some way, shape, or form. Okay, and so then if you wanted to compute, like, let's say the natural log of 17, you are going to try to expand around, pick A to be kind of near 17. Okay. So I guess it's going to have to wait till tomorrow for you to see, like, what happens with this stuff. So a lot of these types of questions, okay, well, if I'm trying to compute, like, and let's say I use, let me just give you the what power of E is closest to 17? Okay, so now this is another if-then statement that you start running. Okay, so the natural, oh, my friend is jacked up. Okay, so the natural log of 17 is, come on, calculator. Natural log of 17, 2.83. Okay, so for reasons that'll become clear tomorrow, we're going to let A equal E cubed. Okay. And so the natural log of 17 is then going to equal this sum, n equaling 0 to infinity, -1 to the n. Then it's going to be 17 minus E cubed to the n plus 1 divided by n plus 1 times E cubed to the n plus 1. Okay, now the reason for that is because the natural log of E to a number is a number. Okay, so what we want to do is we want to kind of, you would keep track of these things in your computer. So somewhere E is stored in, like my device, probably out to 100 decimal places. Back in when I was in high school, my biology teacher, he had one of the earliest calculators that added, subtracted, multiplied, and divided. And I actually saw on the history of Silicon Valley some documentary that was being run back during the spring semester, where guys at one of those Silicon Valley companies made this calculator that did all this stuff, but the downside is like it cost like $250. But the owner of the company, he thought it was the coolest thing, so he said, well, let's just produce them. And then all these rich people started buying them. Well, somehow my high school biology teacher had a hold of one of these things, okay? And so in that device, maybe E was only stored out 20 places or so. Who knows, maybe 30, okay? And then you know how you program your device to multiply numbers together somehow, some way, okay? And then you get this kind of stuff. Okay, so the point is that if we want to compute the natural log of a number, a decision has to be made in our device as to what series we need to use. Which value of A do we need to select? Okay. All right, so let's see here. Let's see. Let's do this. Find a power series representation for this guy. Okay, so we'll do, for example, I'm trying to find ones that are actually, you know, useful. For example, okay, so let's try to approximate the integral from 0 to 0.4, the natural log of 1 plus x to the 4th. Okay, so what we need to do is come up with some kind of an approximation for this. And we want this to be accurate with our error. In the book, he says less than 6 decimal places. Six, 7. Okay. Right, I wasn't paying attention. Hey, walk drop. How the bases get loaded. Oh, those weren't down. Okay, so the solution here. So let's let our f of x be this natural log of 1 plus x to the 4th. Okay, so the derivative of this thing is going to be 1 over 1 plus x to the 4th times the derivative of the inside. So I'll put a 4x cubed right here, and this is going to be 1 over 1 plus x to the 4th. So this is going to be 4x cubed. Now we use our geometric series thing, 0 to infinity, and it's going to be negative 1 to the n, x to the 4n. which is equal to the sum from 0 to infinity for -1 to the n, x to the 4n plus 3. Okay, so that means that f of x, which is the natural log of 1 plus x to the 4th, is the integral of this guy, 0 to infinity 4 -1 to the n, x to the 4n plus 4 divided by 4n plus 4 plus a constant c. When x is 0, the log of 1 is 0, so the c is equal to 0. And so our final form of this thing, before we start hacking around with it, is going to be the sum from 0 to infinity, -1 to the n, x to the 4n plus 4 divided by n plus 1. Okay? Okay, now the problem was to integrate from 0 to, I think, 0.4 or something like that. I don't know why that. The natural log of 1 plus x to the 4th. Okay, now if we could actually do this, something popped up. So if we could do this, we would just do it, all right? But quite often in math, you're going to see in your future, you have to approximate integrals. Okay, so here's our first approximating of an integral by doing something other than Simpson's rule or the trapezoid rule. Okay, this integral is the integral from 0 to 0.4 of the sum 0 to infinity, -1 to the n, x to the 4n plus 4 divided by n plus 1. Okay, the result says that I can integrate each thing term by term. And so it's going to be the sum from 0 to infinity, and it's -1 to the n, x to the 4n plus 5 divided by 4n. That's fine. Somebody's got an echo. Hold on a second. You guys are echoing, so I have to use echoing. There. Now go back to the shared screen thing. Okay, so here's my integral, and then times the n plus 1, and I have to evaluate it at 0 and 0.4. So that's 2/5. Okay, so this is the sum, n equaling 0 to infinity, -1 to the n, and then it's going to be 2/5 to the 4n plus 5 divided by 4n plus 5, and then times n plus 1. And could probably do something more with it here, just to make it look a little bit nicer. Okay, -1 to the n, 2, raised to the 4n plus 5 power divided by 5 to the 4n plus 5 power times 4n plus 5 n plus 1. Okay, now this is an alternating series. It's going to converge because these things are decreasing, the positive guys are decreasing down to 0. Okay? So in the alternating series test, we know that the remainder is less than the n plus first term in the alternating series. Okay? So if we try to pluck out what bn plus 1 is, okay, now you have to be kind of careful here, literally plug it in. 2 to the 4 n plus 1 plus 5 divided by 5 to the 4 n plus 1 plus 5, close. And then 4 n plus 1 plus 5. And then this is going to be n plus 1 plus 1. Okay. All right, so let's see here. So this is going to be equal to 2 raised to the 4n plus 9 divided by 5 to the 4n plus 9. And then this is going to be 4n plus 9 n plus 2. Okay, so now what we want to do is we want to set this less than that 2, 3, 4, 5, 6 decimal places of accuracy. Okay, now this is stuff that you just have to experiment with. Okay, so what I'm getting is 2 to the 4n plus 9 divided by 5 to the 4n plus 9 for n plus 9 n plus 2. This guy needs to be smaller than 10, let's see, 1 0, 2 zeros, 3 zeros, 4 zeros, 5 zeros, 6 zeros, 7 zeros. So 1 over 10 million. So then when you flip this over, did I do that right? 0.1 when you flip it over is 10, 100, 1,000, 10,000, 100,000, a million, 10 million. So that means that 5 raised to the 4n plus 9 times 4n plus 9 n plus 2 divided by 2 raised to the 4n plus 9 has to be larger than 10 million. Okay, so you just start experimenting. Okay, so let's use n equals 1. Let's just see what happens. So go here. So 5, let's clear everything. 5 raised to the 9th power. Then multiply that by when n equals 1, if n equals 1, should write that down here, n equals 1 situation. Okay, so it's going to be 5 raised to the 13th power, 5 raised to the 13th power. Okay, so that's already in the billions. Okay, now I'm going to multiply by 13, and then I'm going to multiply by 3 equals, and then I'm going to divide by 2 to the 13th power. And what I get for n equal 1, I get 5,811,452. So 0.86 or something like that. Okay, so that's not bigger. So now I'm going to have to use n equals 2. So when n is equal to 2, that's going to be 5 raised to the 17th power equals, I'm going to divide out by 2 raised to the 17th power. And then this might do it. If I multiply then by 17, I did it. Okay, so n equals 2 works. Okay, so now we got to go back up to our sum. Okay, so there it is. And it's a fucking mess. So n equals 2. So let me shrink this. So back in my sum, let me erase all this. So back in my sum, I've got the sum starting at 0, going to infinity, -1 to the n, 2 to the 4n plus 5, divided by 5 to the 4n plus 5, 4n plus 5, n plus 1. Okay, now I want to, am I back at 100%? Let's see. There. Okay, so what we want to use here is S2. So S2 is the sum k equaling 0 up to 2 of this -1 to the k, 2 to the 4k plus 5, divided by 5 to the 4k plus 5, 4k plus 5, n plus 1. Is it n plus 1 or n plus 2? Oh, it's b sub n plus 1. Okay. Okay, so when k equals 0, it's going to be 2 to the 5th power divided by 5 to the 5th power times 5. When n equals 1, then it's going to be minus 2 to the 9th power divided by 5 to the 9th power times, k is 1, right? So when k is 1, that's going to be a 9 times a 2. And then plus, when n is 2, that's going to be 2 to the 13th power divided by 5 to the 13th power. And then 2, 8, 13 times 3. So I'll clean this up a little bit. That's 5 times 2/5 to the 5th power minus 1/18 times 2/5 to the 9th power. Now I see why I used 0.4. Okay, then it's going to be the 2/5 to the 13th power. Whoops, that equals. Then it's going to be plus 1/39 times 2/5 to the 13th power. Okay, so let's get a handle on this number here. See what we get, clear everything. 0.4 raised to the 5th power equals, then we'll multiply that times 5 equals minus 0.4 to the 9th power times 18, 1 over. Did I do minus or plus? Let me start over. Okay, so I'm going to have 0.4 to the 5th power times 5 equals, then minus 0.4 to the 9th power times 18, 1 over, and then plus 0.4 to the 13th power divide by 39 equals. I don't even know where this calculator sucks. So anybody have an analog calculator? My iPhone calculator blows. Won't let me keep track of what I'm doing. Calculators go. Well, anyways, let's try this one more time.
I think it's 0.0511.
Yeah, that's kind of what I got. I didn't trust it though. Okay, one more time. So it's going to be 5 times 0.4 raised to the 5th power minus 18, 1 over times 0.4 raised to the 9th power plus 39, 1 over times 0.4 raised to the 13th power equals, I think I got the 0.0511 number. Okay, so here's what we just did. We used approximation techniques to evaluate this definite integral that didn't have an antiderivative handy for us to use. Is approximately equal to 0.0511. Now, if I can find my Texas Instruments calculator that numerically integrates things, we can see that, you know, my answer on the calculator is going to be pretty close to theirs. This is an example of a series that's going to be converging very rapidly. Okay. All right. Now, before we end the lecture for today, I just want you guys to immerse yourself in all of these problems. So basically what we're doing here is we're manipulating the geometric series. Okay. And any opportunity that we get to do this, we like to do it. Oh, just got a home run. Nice. Of x to the n, because we know the interval of convergence, you know, and it's really easy. Okay. Now tomorrow we're going to start with guys that maybe aren't so easy. Like, for example, what do you do with the square root? You know, is there a way to manipulate the square root into some kind of 1 over 1 minus x? No, obviously. Okay. And we just go back to back. All right. So, stop the screen share here. Back to lecture. Oops. There we are. Everybody is. Let's do that. All right. So we're in a pretty good spot. Tomorrow I'm going to try to do a bunch more of these problems, so you can really appreciate the easy case. And that's what this is. This is the easy case. Okay. All right. So let me look in the chat, see how we're doing on questions and stuff. Heck, in the chat, my friend took Steve's drum before. Steve Drum? Yeah, Steve. We seem to have a really good physics department. I think we just hired a new one. We have a new math professor, Carly Gonzalez. I can't wait to see. Why isn't my fucking mouse working? Can't wait to see how she plays out. So we have all these new support courses, you know, like you can take college algebra, there's support course for that.
Okay.
And none of us full-timers really want to teach those courses, except Andy, and I was actually thinking about it just for load smoothing. But so she came in as like a specialist in those types of things. Now, 4 years from now, when she gets tenured, we'll see if she's still, you know, Tyler Booger gets tenured this year.
Oh.
So when fall starts, he's tenured. So now you're going to see the true Tyler Booger. You know, like is he like the professor on Community? I mean, over the top, man, when he's just all in there. That,
Are you
let's
talking
see,
about
what-
King or the guy who helps him at the very beginning, who loses his job really quick, the psychology professor?
No, I'm talking about, here's where we are.
Okay.
Okay, so apparently this community college has dances and shit, you know. So Shannon and I, she's at Santa Ana College. We're watching this going, yes, don't really have this, but I can see it maybe somewhere in the Midwest.
Yeah.
You know, maybe. And so the statistics professor just out of nowhere just broke up with Winger.
Oh, okay, I got you. I know what you're talking about.
Okay, so we're still in season 1. There's like, I think we're at the 18th episode of season 1.
Yeah, it's either 18 or like 24. Generally, they do season episodes for like big TV shows in 6s.
Yeah, I think we're gonna have a lot.
It's pretty great till about 5. I would say 1, and I think it even gets funnier in 2 and 3 and 4. But it's a great show, man.
What's the Senior?
Oh, Chang?
Senior Chang, and they're both Jewish. Him and his brother, they're Jewish, right?
Oh, see
His brother's a rabbi.
Oh, okay, yeah, I kind of do remember that subplot. Now that dude's the guy from Hangover. He actually did like stand up. He was a doctor before he got that role in Hangover. So
is he an MD or PhD?
I can't. I'm pretty sure it's MD, but I I think he was an OBGYN, or I can't remember. He has a stand-up. It's not that great because most of the stand-up is just talking about how he was in The Hangover and then jokes from The Hangover. So it's
You're talking about the Asian guy, right?
yeah.
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 What's his name? Goodness.
Can't remember
Ken,
his name.
Ken,
Ken
Ken
Jeong.
Jeong.
Yeah. Yeah, he's really funny, but I believe he was an MD.
I hope they don't pull that show down because Chevy
Yeah.
Chase as the over-the-top racist bigot
Yeah,
chauvinist is so funny.
it is really
You
funny. They already took out one episode, so we'll see what happens for the rest of the show. But yeah, it's whatever, man. I